All right, let me talk through this assignment briefly. This first section here, where it says, recall the definition of the Mandelbrot set. This is the definition we've been using, starting with this function z squared plus c. First you take the value c, then you apply the function to c, then you apply the function to that value, and so on down the line. This fcn represents n applications of f to the value c. Now notice that we could actually begin this sequence with 0. If we begin the sequence with 0, then the next term would be c. So you could think of this sequence as starting with 0, but we'll just leave off the 0. So the Mandelbrot set is the set of complex numbers such that this sequence does not diverge to infinity. Right, so we saw that before. Now I'm going to use this notation that the nth term of the Mandelbrot sequence is called Zn. Okay? So there's an inductive definition for Zn. Zj plus 1 is Zj squared plus c. All right? So that's kind of review, just some new notation to describe what we've been doing. Now, there's a question. When we actually plot the Mandelbrot set, we only look and see until the function iterate goes, the absolute value becomes bigger than 2. Actually, this should be Zn. Let me just change that briefly. Okay, should be able to do this. Or let's say, yeah, right. Okay, all right. So in this section, in these exercises, we'll answer this question. And there are 3 things that are proven that together show that once the sequence becomes greater than 2 in absolute value, then it will continue to increase. So first of all, we consider the case where c itself is bigger than 2. And then you can show mathematically that the function applied to c will have absolute value greater than the absolute value of c. All right, so if the value of c is big enough, then the function applied to that value will be even bigger. All right, so this is a step-by-step outline of the proof. Read through the steps and try to translate those into equations. All right, so write a proof as you've written proofs before. You statement and reason. That's the usual form for a proof. All right, so that's the first thing that's proven. Second thing that's proven is the supposition now is that the absolute value of z is greater than 2, but the absolute value of c is less than or equal to 2. All right, so it's different from this one. In this case, c was greater than 2. Now, in this case, z and c are different. You notice when you do the Mandelbrot sequence, when you apply the function successively, when I apply fc here, I'm not applying it to c, I'm applying it to another complex value. But this is still a complex value that I could write as z. Okay, so fc of z is applicable here. So this theorem, when I notice that fc of z is greater than z, what that would mean in terms of the Mandelbrot sequence is that if you apply fc to one term in the sequence, to obtain the next term will be bigger than the previous term, right? Because successive terms have this form z, then fc of z, right? Or, for instance, we have zj, and then fc of zj is zj plus 1, right? So then the third, show that these 2 statements above imply that if the nth value has absolute value greater than 2, then all subsequent values will be greater than 2. Sorry, interrupted by a phone call. So I think I was here. So you want to show that these 2 statements are enough to show that once the Mandelbrot sequence gets absolute value bigger than 2, it will always keep increasing. All right, so you can consider 2 cases. This should actually be absolute value of c. Let me fix that also. And this should be absolute value of c. Okay, and in order to make this relation a little bit clearer, I'm going to put this like this so you can see that when I'm applying 2, I will be applying it to the nth sequence, and nth iterate of the Mandelbrot sequence. Right. So see if you can put 1 and 2 together to get 3. All right. So that shows why we iterate the function until the absolute value of z is greater than 2. All right. Actually, this n should be inside rather than outside. Sorry about that. Let's fix that too. Let's see if I can fix it. Looks like I'm having a little trouble fixing this. All right, so let's just do it this. Z, n. There we go. All right, so we'll do that. All right, so let's go on to the next series of questions. It says, why the cardioid shape and circles? So you remember that the Mandelbrot set has this cardioid shape right in the middle. Now, some of these we've done in class, you don't need to do again. These were algebraic problems. For a given c, find all values of c such that fc of z is equal to z. These are called the fixed points. And what happens is that if you start at c and you keep taking f of c, f of c, and so on, eventually it will either go to infinity or it may go to a fixed point. Once it reaches a fixed point, it will stay there. Because, for instance, if zn is a fixed point, then fc of zn is also zn. So that means zn plus 1 is a fixed point. Okay? So once you reach a fixed point, as I said, you get stuck there. All right? Now we also did this. We found an expression for fc of z plus delta minus fc of z and used that to compute what is basically the derivative. And the answer you got was z, I believe, something like that. So you may denote that as, so that's the complex derivative. So let's consider what the implication of this complex derivative is at a fixed point. All right. So if z is a fixed point of c, and the derivative, the complex derivative of z is less than 1, then it turns out, and you showed this in class, that if you take some number close to z, which we call z plus delta, it's a number close to z, and apply fc to it, then the result fc of z plus delta is even closer to z than z plus delta. In other words, if I take a point close to z plus delta, apply fc to that, then it gets even closer. Now, if I applied fc to this value, it will become even closer. Apply fc to this, it will become even closer still. So that means that once you're close enough to z, you keep homing into z in successive terms in the Mandelbrot sequence. So you can say that this point z attracts successive terms in the Mandelbrot sequence. All right, so that's what this is saying. So we talked about that in class. All right, as it says, that this sequence will become closer and closer to the fixed point z. Such a fixed point is called a stable fixed point. So the question now becomes, for what values of c is the fixed point of the Mandelbrot map a stable fixed point? Okay, so for what values of c, remember for each different c, we're going to get a different Mandelbrot sequence. And if that Mandelbrot sequence has a stable fixed point, that would mean that the Mandelbrot sequence would not escape to infinity, but it remains bounded. It goes to the stable fixed point. At least we can, that's reasonable to suppose. All right. So you found a formula for the stable fixed points before. So you did that before. Don't need to do it again. I believe this is right. You can double check it. And then from this shouldn't be 7. This should be 6 because it's the previous problem. Let me see if my numbering is correct here. I guess it's 6, yes. Okay. Or it's not 6. Let's see which one it is. It's from... okay, yes, yes, that's right. Okay, it's from 6. It's from the previous one. Okay, so that means that as long as absolute z is less than 1/2, then the fixed point at z will be a stable fixed point. But the fixed point depends on c in this manner. Okay, so we plug in this value for z, and we get this result. Okay, so the fixed point for the point c is stable if and only if this result happens. Now, you remember that absolute value in complex numbers is not the same as absolute values in real numbers. this, and also this is going to be a region because it's an inequality. So usually inequalities specify regions. So the boundary of this region will be the set where the equality holds. Just like if you have x squared plus y squared less than 1, that's the interior of a circle, and the circle is x squared plus y squared equals 1. All right? So we want to find the boundary of this region where the C produces stable fixed points. So the boundary is where equality holds. Now, the absolute value of a complex number isn't just plus or minus. In this case, if the absolute value is equal to 1/2, that means that this point lies on a circle with radius 1/2. That's how complex numbers work. The absolute value is the radius of the complex number in the complex plane. So the fact that this has absolute value 1/2 means that this number lies on the circle of radius 1/2. Let me write that also. Okay, I'll just write that in this part here. That this number here lies on the circle in the complex plane of radius 1/2. All right. Now, if it lies on the circle of radius 1/2, that means that we can write it in this way. Instead of e to the I theta, maybe I should say, instead of this, I should say 1/2 cis theta. I can do it that way. Maybe that's more familiar. All right. So this is cosine theta plus I sine theta. This is a point on the unit circle. So if I take 1/2 times a point on the unit circle, that's a point on the circle of radius 1/2. All right. So this equality here is the same as this equality here. But theta can take any value from 0 to 2 pi. Right? So that's that gives the points on a circle of radius 1/2. Right. Maybe I should draw a picture here. Just pause for a moment. All right, here's the picture in the complex plane. When you have the complex plane, the x-axis is the real part, and the y-axis is the imaginary part. If I take a circle of radius 1/2, if I have some angle theta, I didn't draw the theta, let's do that. Okay, so theta would be here, from like this. Okay, and so this angle here is theta. Okay. Now, if I have an angle theta here, that means that this point is 1/2 cis theta, which is defined as 1/2 times cos theta plus I sine theta. Okay, so that's what we have here. Now you can also write this as 1/2. Sorry, equals 1/2. You write it as e to the I theta. That's another way that it's written. Okay. Right. So you can write it that way. All right. So let me go back to the document. All right, so you want to solve this equation for C to get C as a function of theta. So that will give a curve in the complex plane in parametrized form, where theta is the parameter. You've seen parametrized curves before in calculus. Sometimes your parameter is t, sometimes it's theta. When you do polar graphs, that's how you do a polar graph, is you do r as a function of theta. Now in this case we have a complex number as a function of theta. So when we plot the set, we'll be choosing different values of theta and plotting the different values of z that result from the different values of theta. All right, so that's this part here. It says for 100 evenly spaced values of theta from 0 to 2 pi, plot the values of c of theta. That c of theta is obtained up here. So notice in your plot, you should be plotting the real part of c on the x-axis and the imaginary part of c on the y-axis. Okay, so theta is not on the x-axis, it's the real part of c that's on the x-axis. Now take a look at the shape that you obtain and try to draw some conclusion. And you can make your conclusion as a comment in your code. All right. So previously we looked at the case, in class we did this, we looked at the case where the points C were on the circle of radius 0.2, which is inside the cardioid. Now, we saw that in this case, all the points, if you took a Mandelbrot sequence at any of these points, it did converge to a single point. So all of these points had a stable fixed point. So in fact, that tells you that all of these points are inside this region. Now, let's look at some other areas of the Mandelbrot set. The circle of radius 1/4 centered at 1 is also part of the Mandelbrot set. I'll show you that. That's this circle here. This circle actually has center at -1 and radius 1/4. So I want to see what happens to points inside that circle. And I want you to create 3 plots. On the first plot, show all terms of the Mandelbrot sequence for 16 points, for 16 points on that circle. Okay, so you'll be showing the Mandelbrot sequences. Let's see, I shouldn't say all terms. I should say, let's just say something like 30 terms. That's okay. This plot will be similar to what you did in class for this circle. And you'll see a set of points. Now, each series of points should have a different color. So the series of points for one of these points should have one color, and the series of points for another point should have a different color. So in other words, the plot here should be very similar to what you see here. But you're going to see something different happening. I'll just give you a hint. These series are not going to converge to a single point. All right? So I want you to create a second plot. And you can use, if you want to, you can use figure 2 in Python if you want. And then you should show only the even terms in the sequence. Okay, so you're not going to show all of them, just half of them. And then on the third plot, show only the odd terms of the sequence. Okay. All right. All right. So you'll get 3 plots for this circle. And then once you've done it for this circle, it's easy to do for a couple other circles. So you can do a separate series of 3 plots for this circle and for this circle. And explain what your plots are showing about the behavior of the Mandelbrot sequence for points within this circle, C plus 1 equals 1/4. Right? So we want to get some idea of the behavior of the Mandelbrot sequence for points inside the this is actually called a bulb. It's this circle here. Okay, so you'll see something very significant. All right. All right. So for the next two exercises, you use the following reference, and let me just go there so that you can see it. Well, I'll just copy it. It doesn't seem to be going. Copy that and see what it looks like. Where is my browser? I don't see my browser anywhere. I have to bring it up. All right, let's bring it up. I'll just bring up Firefox, I guess. All right, so here's the page, and it gives some more background on Mandelbrot set. I think you'll be interested in that. And here's various pages that it links to, and these first 4 pages will be interesting for you as far as doing this assignment. So specifically, I'll be referring to this one. And it talks about some of the patterns and how they relate to the behavior of the Mandelbrot sequence. Okay, so you can take a look at that. Right. So you'll be looking at that. And then there are 2 more exercises here. So you'll have to look at that reference. It says use the reference to locate a bulb or decoration of period 3. Locate 3 points inside the bulb and make 4 plots. So this is going to be similar to what you did for the circle centered at -1. We want to look at the behavior of the Mandelbrot sequence inside this other region of the Mandelbrot set. And you're not going to be plotting every point in the sequence, but in this case you'll be plotting every 3rd point. Now, of course, there are 3 sequences that have every 3rd point. You could start at 0 and take every 3rd point. You could start at 1 and take every 3rd point. Or you could start at 2 and take every 3rd point. Right? And so I want you to plot these 3 on 3 separate plots. besides doing all the terms together. Okay, so this one is going to be very similar to the one you did here to number 10. So it's just, you can just copy and paste your code. Right. Now finally, there's another set that's closely related to the Mandelbrot set. It's called a Julia set. Right. Now, it may look like the Julia set has exactly the same definition, but it's not. Notice that the Julia set starts not with C, but with Z. And Z can be any complex number. So in other words, for one particular value of C, you can choose many, many different values of Z. And the Z for which this sequence remains bounded is in Julia set. And if it's not bounded, then it goes outside the Julia set. So you can see that in some ways it's similar to the Mandelbrot set, but it is subtly different. Okay, so what I want you to do is modify your Mandelbrot code to plot the colored Julia set. So you're going to plot the index just like you did with the Mandelbrot set, and you'll get something like this for the value of, in this case, well, let me see if I gave you the value. Oh, here I gave you the value for C. For one value of C, you're going to have several values of Z. Z will be in the square that has side 2, so where the x and y are the imaginary parts, real and imaginary parts of the complex number. So for instance, this point here is 2 plus 2i. This is 2 minus 2i. This is minus 2 minus 2i, minus 2 plus 2i. And then you can plot, say, 200 points across, 200 points down. Use ImShow just like you did before to find the colors, but you're going to define your loops a little bit differently, and of course you're going to get a different result. You may not duplicate these colors, but the idea will be roughly the same. All right, so I hope that's a good introduction, and I will be holding a session on the weekend to give you more insight. All right, hope that works for you.